Okay, so as promised, I'm going to go over this answer key and give explanations for the answer choices. This first video I'm making is just going to go over questions 1 through 19 at first. So if you weren't here the day that we did those in class and or you just want to review, this video is just going over 1 through 19. Following this video, I'll be doing the rest of the answer key in sections as well. I'll title it accordingly, so just skip to the section that you need. But let's start with numbers 1 and 2. And I know it's kind of small because I have mine printed out in the small version that you guys put in your notebooks. But follow along with your copy of this that you have as well. So numbers 1 and 2, there's not too much explanation there, right? It's just basically asking you for the definition of an acid and a base in terms of the Bronsted-Lowry acid-base theory. So if you remember in class, we went over the 3 main types of acid-base theory. I'll kind of show my notebook here real quick. But we learned about the Arrhenius acid-base theory, the Bronsted-Lowry one, and the Lewis acid and base theory as well. These notes are up on Classroom if you were not in class. But this first question is specifically asking for the Bronsted-Lowry acid and base theory. So by definition, an acid is a proton donor. And another way to say that is an H plus donor. And we talked about it in class, but the reason H plus is the same thing as a proton, because I'm going to write on here really quick, H plus donor. That's saying the same thing, because a normal hydrogen atom that's neutral has just 1 proton in the center in its nucleus and 1 electron. There's no neutrons in regular hydrogen. And H plus, that's just hydrogen that's lost an electron. So if regular hydrogen just has 1 proton and 1 electron, then H plus, once it's lost an electron, it's essentially just a proton that's floating around. Hence why H plus is called a proton. So that's just kind of finding the definition based on the one that we did in class. Second question here is asking, okay, in the Bronsted-Lowry definition of acids and bases, a base, and that would be the proton acceptor. In other words, that is the H plus acceptor. So that will be the molecule that takes on H plus and goes up by 1 H plus, as we'll see here in a second on number 3. So number 3 gave us an acid and base and a conjugate acid and a conjugate base. And it wants us to look at the following equation here and identify who the acid reactant is and the conjugate base that it made. So just to kind of review from class, we have to remember that like an acid turns into a conjugate base, and a base turns into a conjugate acid. And what those are, you can think of it this way. The conjugate base, that's just kind of the fancy name for what the acid looks like after it loses its hydrogen. Because again, the acid will lose H plus. So the conjugate base is just what the acid looks like after it's lost the H plus. And the conjugate acid, you can think of it as a fancy way of saying this is what the base looks like after it has gained the H plus. Because again, a base's job is to be a proton acceptor or an H plus acceptor. So looking at this following formula here, and I did write it out kind of big for you guys on a different sheet of paper. Well, how are we going to be able to tell who the acid and who the base is, and who the conjugate acid, who the conjugate base is? Yeah, the question's only asking for the acid and its conjugate base, but we'll kind of label all of them just to make sure you guys are familiar with being able to identify any kind. But according to the Bronsted-Lowry theory, an acid and a base that react in the Bronsted-Lowry acid-base theory, the acid will turn into its conjugate base and a base will turn into its conjugate acid. So we're just going to look at the equation here for number 3. And I'm going to look at the 2 products that were made, and I'm going to ask myself, right, which one of these looks like one of these, but it's just short in H plus. So in other words, you can look at the 2 reactants and just say, which one of them lost H plus by looking over here. And we can see that, hey, this one right here looks just like this one, except it went down by 1 hydrogen and it went down by a charge of +1. So that would tell us that this had to be the acid and this has to be the conjugate base that it made. So again, an acid by definition in this theory has to lose H+. And oh look, here it is when it loses H+. So this is the conjugate base. Again, I told you before, think of the conjugate base as just what the acid looks like after it loses the H+. And we talked about this in class, but I'll review it for people who weren't here. But we went over, why is this called a base in the first place, right? Like, why does an acid make a conjugate base? Well, this molecule right now, right, it has a charge of -1. It's a little upset, right? This molecule wants to be the acid, but it's a little upset now because it lost an H+. So what this one is going to do is it's going to try to gain the H+ back so that it can revert back to that acid. But technically, right, by definition, if you gain an H+, you by definition are a base of some kind under the Bronsted-Lowry acid and base theory. So that's why this is called a base. It's because when this reaction goes in reverse, this will be the molecule gaining H+ in order to revert back to the original acid. So then this would be our answer choice on the test as letter A, right? We just identified that acid and that base here, so I'll kind of label it on here too. But that was our acid, and here was the conjugate base that it made. But let's just double check and look to make sure that this one is following the definition of what a Bronsted-Lowry base should be doing. And a Bronsted-Lowry base should be gaining H+. And if you look at these two here, these two molecules look identical, except this one over here has an extra H and an extra positive charge. So this one here represents this base once it's gained the H+. So this is that conjugate acid of this base here. And again, why is this called an acid at all? Well, when this reaction goes in reverse, which all these do because they have to wait until equilibrium is established, NH4+ now, right, it's a little upset because it just gained an H+, and it doesn't want the H+, right? It doesn't want to have a positive charge if it can avoid it. So what this molecule is trying to do is revert back to the neutral NH3. So this thing is going to try to lose the H+ that it just gained. And by definition, if you lose an H+, you are an acid of some kind. So when we go in one direction, here's our acid, here's our base, right, making these two products. And then when this goes in reverse, right, now this is serving as the acid, and this is serving as the base. And this guy over here will give his H+ back to him, and we'll end up back with our two original products, or excuse me, our two original reactants. So going on to number 4, in the following reaction in aqueous solution, the acid reactant is blank, and its conjugate base product is blank. So again, we're going to do the same thing that we just did in the top question, looking at, well, which one of these lost an H+ and which one gained an H+. So I'm looking at the two products that formed to look at which one of these looks like one of these, but that lost an H+. And I see that these two here, right, the only difference between them is this one over here looks just like this one, but minus an H and minus a +1 charge. So this one has to be my acid, and this has to be the conjugate base that it made. Because again, I'm just going to subtract the H and subtract a +1 charge, hence why the charge went from -1 to -2. And then it doesn't ask for it, but just to verify, that would mean that this should have been our base, which means that this is the conjugate acid. And let's look at it to make sure. Does this one over here look just like our reactant, but this one is with the extra H+, which it is, right? We see this one had just the H2 on the end. This one has the NH3+, so this thing gained an H+, so that is the conjugate acid of that base and that problem. So number 4 would be option D, because this was our acid, and that was that conjugate base that was made. Okay, so going on to number 5, which of the following is the conjugate acid of the hydrogen phosphate ion, HPO4 2-? So the trick with this question is, it's asking you who the conjugate acid is. So then we have to ask ourselves, well, who is it who makes a conjugate acid? Does an acid make a conjugate acid, or does a base make a conjugate acid? And like we talked about before, right, it's the base that creates the conjugate acid. So this was kind of your hint in number 5, that this hydrogen phosphate ion is technically a base, because only a base can make a conjugate acid. So now what you have to think of is, right? I have HPO42 minus. And if it is a base, its job is to gain H plus. So then you have to ask yourself, what is this guy going to look like once he gains the H plus? Because that's what a base is going to do. It's going to gain H plus. So instead of having one hydrogen, it's going to have two hydrogens. I'm going to keep the PO4. The charge was 2 minus before, but it just gained an H plus. So we just added an extra positive 1 charge, bringing this charge to -1. So the answer for 5 is B. Okay, so going on to number 6. These are all kind of pretty quick here. But which of the following is not a conjugate acid base pair? So in order for you to identify a conjugate acid base pair, you want to just think of how we've learned them, because we're only doing monoprotic acids, which are just acids that only lose 1 H plus. You are going to be able to identify the conjugate acid base pair, because any conjugate acid base pair should only differ by 1 H plus. So looking at all these answer choices, right, NH3 to NH4 plus, right, that's different by just 1 H plus, so that qualifies as a pair, right? This would be a base, and that's the conjugate acid, right? This one down here, that's not the right answer. This one lost an H plus, so that one qualifies as well. This one up here gained an H plus, so that qualifies. This one lost an H plus, so it qualifies. So the only one that doesn't qualify is the H3O plus to OH minus. And why is that? Well, because again, they can only differ by 1 H plus. So if you look at H3O plus, well, if that were to lose 1 H plus, which by definition it would have to in order for it to be considered a conjugate acid base pair, that would turn into neutral water. And then that one can lose another H plus to become the hydroxide ion. But this requires like a 2-step deprotonation, and a conjugate acid base pair would just be different by 1. So that's why B is the answer choice, because H3O plus, or the hydronium ion, and the hydroxide ion differ by 2 H pluses, which disqualify it from being a conjugate acid base pair under the Bronsted-Lowry acid base theory. So we're going to keep the same kind of logic all the way through 7 through 9 here. So 7 is just asking which of the following is a conjugate acid base pair. So 6 was which one it's not. 7 is asking which one is. So you're just going through and locating which of the following pairs just differs by 1 H plus, which would be A. Same thing with 8. 8 is asking which of the following is a conjugate acid base pair. So we're looking for a pair that just differs by 1 H plus, which is why C is the answer. And 9 is worded like number 6 was, which of the following is not a conjugate acid base pair? That would be B, because that one is different by an oxygen, and by definition we have to be differing by an H plus. So 10, right, the stronger the acid, the weaker the conjugate base. So that answer choice there is B. I didn't circle it very well, but that is B. And I guess I can go over real quick why that is, in case you're reviewing this because you weren't in class or didn't understand it the first time. And it's probably good that I review it now anyways, because some of the questions on the next page require you to understand why this is. So let me use an example of a strong acid. A strong acid is hydrochloric acid. So when this dissolves in water, we're going to end up with the H plus. Sorry, I'm turning this a little crooked here. We're going to end up with the aqueous H plus ion and the aqueous chloride ion here. So let me kind of label this a little bit for you. But here's my original acid, right? H plus is that important product that comes off. It's the proton that comes off. And this technically is the conjugate base of that acid. So a strong acid, like we reviewed in class, is one where the equilibrium is shifted clear to the right. In other words, a strong acid is an acid that's good at doing its job. And what's the job of an acid? Well, the job of an acid is to produce H plus. So a strong acid is one that when it dissociates or breaks apart into the two products, it's going to stay broken apart. These two here are not going to have the ability to rejoin And because if it did, right, it would be shifting back to the left and it would be reforming this acid again. A strong acid, we assume that this is basically like 100% dissociation, right? Where we know that once the HCl breaks up into the H plus and Cl minus, it's not coming back together again, which is why this is considered a strong acid. It's really good at producing H plus because every H plus that comes off is staying H plus because this chloride over here is never going to be able to combine with it to make the acid again. So why is this a strong acid? Like, why is this acid never able to reform? Well, it's because this conjugate base is a really bad base, right? The job of a base, right, by definition in this theory, a base is a proton acceptor, right? A base is supposed to be really good at gaining H plus. So Cl minus is not good at gaining H plus, right? That's its job as a base, is to gain H plus. It's to accept H plus. So if this acid breaks apart and stays broken apart, it must be because this chloride ion is not doing a very good job recombining with this hydrogen, right? So since it's doing such a bad job, these two are never able to find each other again, which means this acid over here is staying broken up into these two things that formed. So an acid, a strong acid, maybe I'll put strong here so that we remember that, is pretty much strong by virtue of its conjugate base being such a bad base. Like, so bad, in fact, that we wouldn't even say Cl minus is even basic at all, because a strong acid 100% dissociates, right? We're saying that none of this gets back together. So Cl minus can't even do the job of a base at all. It's not good at all of getting H plus. It cannot do it at all because 100% of this stuff stays broken up. So we wouldn't even consider this conjugate base to even be basic because it can't even do its basic job of gaining an H plus. So that'll come in important again on the next page of questions, but that's why a strong acid has a weak conjugate base. And obviously then it would make sense that a weak acid has a strong conjugate base, right? A strong base has a weak conjugate acid, and a weak base has a strong conjugate acid. So they're always kind of flip-flopped and indirectly related to one another that way. So number 11 is asking, ammonia, or NH3, acts as a weak base in aqueous solution. What is the acid that reacts with the base when ammonia is dissolved in water? Well, water is that special molecule that can act as an acid or as a base. So when you take ammonia and dissolve it in water, water is going to be the thing serving as the acid in that case. Water will be donating the H plus to the ammonia, hence why B is the answer for 11. 12, it's worded kind of trickily. However, what it's basically getting at is, like, when we think of the KB expression that we derived in class, right? We came up with the KB expression ourselves because we talked about how any equilibrium expression is the products divided by the reactants. So we looked at the basic equation for a base dissolving in water, which is this one up here. This is the one that we had in class, right? Some base, right, gets dissolved in liquid water, and it's going to produce, right, the conjugate acid, or the BH plus, and we're actually going to get the hydroxide as a result of the water. So this is the basic equation that we even used to derive this KB equation. So we did the products, which were these two, over the reactant, the base. And again, we didn't include the H2O as one of our reactants because we don't include liquid or solid reactants or products in the equilibrium expression, because, right, it's the aqueous ions and those aqueous molecules that are responsible for this back and forth, back and forth, back and forth, because they can break up, reform, right? They can, so they reform the acid, they can break up again and form this, and then they can reform back to this back and forth, right? It's only those aqueous things, which is why we only care about the aqueous ones. But the KB expression, like, this is the official KB expression that you'd find in a textbook or find online. So what that question is asking you basically is, what is the equation that this is based off of? Like, where did we get these as the products and this is the reactant? Well, it's based on this one. It's the same one that we did in class, which is why C is the answer here, because our KB expression was, right, the products, the concentration of the products, excuse me, over the aqueous reactant, which was the base. So that's just asking, again, which chemical equation did we even derive the KB equilibrium expression from? And that is a minus sign. It kind of looks like a plus, but you guys know that hydroxide is charged with -1. Okay, so moving on to number 13. which of the following is a strong acid? So we talked about in class how, there'll be a way for us to calculate a strong acid because all strong acids will have a Ka or a dissociation constant that's above 1. But just for quick reference, it's, I've never taken a chem class where we did not have to have these memorized, but I did give you guys in class a list of the strong acids and the strong bases. So here's our strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. And for strong bases, we have lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So, I just have these memorized. Again, every chem class I've ever had to take, they expect that you know what those are. These are ones where we wouldn't even have to bother doing a Ka or a Kb expression to even see if it's more than 1, because these are the acids and the bases where we assume 100% dissociation, right, which is the strongest kind we can have. So 13 was just kind of testing your memory there a little bit and asking which of the following was a strong acid. So that would be the nitric acid, or option A. So same thing with 14, which of the following is a strong one? Again, just testing your memory there of those. So then we'd have perchloric acid, or option E. Which of the following is not a strong acid? So again, just kind of a little memory check. Answer would be C, carbonic acid. 16 is asking which of the following compounds cannot be a Bronsted-Lowry base. So we have to remember what the definition of a Bronsted-Lowry base is, right? It was our answer to number 2. A Bronsted-Lowry base is something that can accept H+, or accept the proton. So out of all the option choices, if we had to pick one, right, we're going to pick the NH4+. That's the ammonium ion, because that thing already has a positive 1 charge. Right, bases have to gain H+. So they're not only going to get a hydrogen, but they're going to be gaining an extra positive charge. So something that has a positive charge already, it wants to become neutral. It doesn't want to become more positive, right? So out of all these other choices that we have here, right, hydroxide that's negatively charged, it wouldn't mind gaining an H+, because it would go back to neutral. Right, this is neutral, this is neutral, this is negative charge, right? So out of all the other choices, right, A, B, C, and E are set up way better to actually accept an H+ charge. Something that has a positive charge does not want another positive charge. Or you can think of it this way, right? We know that like charges repel each other, right? Negative and positive like each other, but positive and positive don't like each other. So that positively charged H+ that's floating around solution is going to want to steer clear of the NH4 because he has the same charge, right? So he's going to deliberately avoid the NH4+, making him less likely to ever be able to accept an H+, which means he's the least likely to be the Bronsted-Lowry base. Okay, so 17 is asking each of the following pairs contains one strong acid and one weak acid except. So if you're not on that list of strong acids, those 6 strong acids, we can assume it's weak because those are the ones that we know will have the Ka/1 and will dissociate 100% of the time. So all you had to do pretty much was just kind of go through the list and find one pairing that didn't have a strong acid, because you can assume every other acid is weak. But the reason that D is the answer is because HSO4-, that is actually technically not an acid. That's what sulfuric acid becomes after it loses the H+. So HSO4-, which is the hydrogen sulfate ion, that's the conjugate base of a strong acid, but HSO4- is not a strong acid itself. That's what the strong acid looks like after it loses the H+. That's the conjugate base of it. And then we have HCN, which is, like I think the colloquial name for it is prussic acid, but that's not on our list. So here we have like a conjugate base with a weak acid, which is why D is the answer. All the other answer choices have one of the strong acids with any other acid, which would be considered weak. So they all qualify. So 18, so this is why I went over like a strong acid having a weak conjugate base and vice versa, because 18 is asking which of the following is not basic. So we're going to say you're not basic if you are not good at doing the base's job. And a basic job means, right, or a base's job means you should be able to gain H+. So then we have to think back to who the strong acids are, because all of these strong acids here make a conjugate base that is so weak, right, it never gains the H+ back. Hence why these acids are strong, because they're really good at producing H+, because the conjugate base can never actually gain the H+ back, right? So then any of the conjugate bases of these acids are like so weak we don't even consider them a base, right? So the chloride ion, Cl minus, right, not basic at all. It cannot do its job of gaining or accepting H plus. The bromide ion, the iodide ion, right, nitrate, the NO3 ion, sulfate, the SO4 ion, and the perchlorate ion, ClO4. So all of those conjugate bases aren't even basic because they can't even do the basic job of gaining an H plus, not even once, right? Because strong acids we assume 100% broke up, and 100% of those never got back together. So you'd have to just kind of scan this list and ask yourself which one of these is the conjugate base of a strong acid, which would be the nitrate ion here, because nitric acid is one of the strong acids. So again, when that dissociates into H plus and the nitrate ion, right, this nitrate does not do a very good job at gaining the H plus, hence why it stays broken apart, which is why the nitric acid is strong. The last one that we'll go through on this video here, which of the following is basic, right? So then we have to pick something that has the ability to actually, right, gain H plus back. So that will be, right, the conjugate base of a weak acid, because those acids are weak because they reform frequently because the conjugate bases are so strong. So A, right, has chloride. Well, that's the conjugate base of hydrochloric acid, which is strong, right? The nitrate ion, right, that belongs to nitric acid, which is strong. Here's the perchlorate ion, which again is a strong base, or a strong conjugate base, excuse me, a weak conjugate base, because it belongs to the perchloric acid. And here we have HSO4 minus, which is the conjugate base of the sulfuric acid. So we have this SO4 2 minus. That would be from when this one here broke up again to create the SO4 2 minus. So this one would be considered basic because this one right here is not a strong acid, right? H2SO4 is strong, but not the hydrogen sulfate ion itself, because this thing can further deprotonate again to make this, but this itself is not considered a strong acid. So, right, this one is, so don't get that confused. You might have seen that and been like, oh, well, that looks like, right, sulfuric acid's conjugate base. No, D is sulfuric acid's conjugate base, right? E is what that can further deprotonate into, so that's why E is our answer for that one. So I'm going to go over the next couple ones in another video, but again, this was just 1 through 19. If you weren't in class and or if you were just trying to review it quickly, I'll make another one right now going into the next couple sections.